Hello, welcome to another video. So in this video we're going to go over a couple inclined plane examples to kind of show you how inclined planes work, because it is a little bit different, you may notice. But as you're doing this, you'll still follow the same sort of patterns, okay? But something kind of unique does happen when we're on inclined planes, and I'll kind of walk you through that. So here we have a box on an inclined plane, and as you can see, this box is going to slide down. Okay, this is a frictionless system. Okay, so we still haven't done friction examples. We'll do those soon. But we want to find the acceleration of a 10 kilogram box on a frictionless incline as shown. Okay, so the first thing we need to do is, like we always do, we want to go through and we want to do the free body diagram. Okay, so this box is on an incline. Okay, and so the incline, right, is kind of like that, and so we're going to be perpendicular to that for the normal force, because the normal force is perpendicular to the incline, right? This forms a 90-degree. Gravity still exists. We're still on Earth, so we have gravity pointing straight down. I'll often see mistakes where people draw gravity kind of opposite to normal force like this, but this is not right. Okay, so don't do that. Now, we've kind of gone through, we've done normal force and we've done gravity. There's no tension in this problem, there's no springs going on, there's no friction, of course. This is basically it for this type of problem. Okay, so this is our free body diagram. So now what we're going to do is I'm going to go ahead and I'm going to create a coordinate system. And the coordinate system that I create is a tilted coordinate system. Okay, so we're going to use a tilted coord system. And the main reason I'm using, how did I do that? So the main reason I'm using a tilted coordinate system is that we want most of the forces and or acceleration, we want most of our vectors to line up on our coordinate system, right? And so you can see the box is going to accelerate this way. So this is our x coordinate right here that follows the acceleration. And we have the normal force on there. Okay, so we have two of the forces that are on a coordinate. Gravity, however, won't be. Okay, but you'll see this kind of forms, this also has an issue with it, which I'll bring up in a second. But as we create our equations, this is the coordinate system that we're going to use. And you always want to create a coordinate system or at least it's easier to create a coordinate system. And so for you guys, because it's easier, I'd say always do it. Create a coord system that has acceleration on one of the axes. Okay. And so we kind of did that here. If we were accelerating in this direction, then I'd probably have the x over there and maybe the y like this, right? So you always want to have one of your axes on a coordinate. Okay. So let's do our equation. We've got our x and we've got our y equation. And so on our x equation, we have, what I'll do is I will write it first and then I'll explain it later. So we actually have, on our x-axis, the y-coordinate of gravity. And so the y-coordinate of gravity is Fg sine theta. Okay? And then we have mass times your acceleration in the x. And our acceleration, again, is down the ramp, fully in the x direction. Okay? I will explain this shortly. In the y direction, Well, we've got the normal force. That's fully in the y. And now, remember what I said before, how if you have one component of gravity or one component of a force in one direction, you must have the other component in your other equation. So we already have sine, so we must have cosine in the y. And so it's going to be negative, okay? So what I'm going to do, so these are our equations that we need for this particular type of problem. And the problem is, or the issue that gets people, is that sine is now associated with x and cosine is now associated with y, which is something that isn't typical, right? I think up to this point, almost everything has been cosine is x, sine is y, and you just get used to it. Right? You know, you have a typical triangle here. This is our whatever, some generic force. This is our x component, this is our y component, and so the adjacent side is our x, so this is cosine, and then our opposite side is sine, right? That's the way it's always been. So now what I'm going to do is show you why it's not the case here. So this is our triangle. So what I'm going to do is I'm going to replicate our triangle, and I'm going to make it larger. So we have gravity that's pointing straight down. So this is just gravity, okay? And now what I'm going to do is I'm going to add in our coordinates. So I'm going to draw in, here's our x coordinate. That's our x, right? And then our y coordinate is this guy, okay? And I'm going to actually draw it, I'm going to draw both the positive, so that's the positive y, and then this is technically the negative y, okay? Because remember, we tilted our coordinate around, right? So you just look at it like that, and that's basically what it is it's tilted now. So we went from this to this. Okay. So now, if I'm looking at this, here is my angle. The adjacent side to this is actually beneath the angle, right? Just like if we were to flip this over and this is our angle, this is the adjacent side. It's beneath it, okay? And so the adjacent side over here happens to be, this is the adjacent side, this is on the y, okay? And so that's why we put cosine right here in the y, because it's the adjacent side, and adjacent is cosine. And if you look at this, okay, this is opposite to it. And this is here's the x, right? This is the x-axis. Remember, with vectors, you can move them back and forth. So a vector down here, you can just shift back and put it right here. Same with this vector, which is our component of gravity. And so this is now the opposite side is now on the x-axis, okay? And so that's why they swap. Opposites on x, adjacent is on y, okay? And so that's why we flip them for the inclined plane. So let's get back to this. I'm going to redraw it so we don't have to scroll up each and every time. Oops. It's Fn minus Fg cosine theta equals 0. And again, it's 0 in the y because we're not accelerating through the incline, okay? We're only accelerating down the incline, which is in this direction, okay? And this is the acceleration direction, which is in the positive x. Okay, so now we want to solve for here's our x equation. I'm going to basically take this guy and I'm going to say mg sine theta equals max. And this is because, remember, f of g equals mg. So we're just plopping that, plugging that in. Okay? So, because mass is on both sides, the acceleration is not a function of mass. Okay? And that's the case because it's frictionless. And so we have ax equals g sine theta. So it's only a function of gravity and a function of our angle. So sine of 30 degrees. And if you remember right, sine of 30 degrees is just 1/2. So this is actually 4.9 meters per second squared. Okay. And so, yeah, that's kind of this problem. There's really not too much to it. The hardest thing is figuring out this incline, okay? Figuring out why the forces flip, okay? And the forces flip because the adjacent side is now on the y and the opposite side is now on the x-axis, okay, with a tilted coordinate system. You could do this problem without a tilted coordinate system, but then you're going to have this acceleration, which is a vector. You have to create components of that. So keep that in mind. Okay. So that's kind of one example with an inclined plane that you can do. So let's do another one. And so here's our system. And so this is going to be another Atwood's machine. Okay. So we've got two boxes. We've got A and B. And because I didn't make them big enough, I'll write it out to the side here. And this is going to be 5 kilograms. And B is going to be 10 kilograms. And this will be frictionless, of course. So we'll do frictionless or friction in the next lecture, but not this one. And so the question goes, solve for acceleration of system. Okay. And of course, this stuff is all massless as well. So the rope's massless, and that'll allow us to use the tricks that we always do. Okay. So the very first thing you need to do is you need to do a free body diagram of both objects. Okay, we have two objects, so now we need to do a free body diagram of both. So this guy is on the inclined plane pointing this way. So we reflect that with the normal force that points up, gravity that points down, and then the tension in the rope is going along the incline. Okay. There's no other forces that I can see there. That's pretty much it. We need to do B. So this is for A. You can add A everywhere. And then remember the tension will be equivalent because it's massless. B, it's just hanging up. So we'll have tension pointing up, gravity pointing down. Okay, so what I'm going to do for my coordinate systems is for individual objects, you can actually create two different coordinate systems. So I'm going to have plus y plus x, and then here I suppose I'll just have down be positive. The x is irrelevant because there's no forces in the x. Actually, let's be somewhat consistent. I'll make down positive for this guy. Okay. Or let's do, nah, let's just leave it like this. I like up as positive, unless they're accelerating down. So let's do that. Okay. So in the x direction, we have f of t pointing in that way, and then we have minus some component of gravity, right? So the component of gravity will be with the y-axis, not with the x, so don't make this theta. That's a common mistake. It's making an angle with the y, okay? And so our theta is right here, and so our x component is opposite, okay? So it would be minus FGA sine, because it's opposite, theta. And that's equal to mass times acceleration. This is positive because it's going up the ramp. Okay. This is technically going to be mass A as well. So in the y, we have FNA minus FGA cosine of theta, and it's not accelerating through the incline. Okay, so FNA minus the adjacent side right here. Okay. In the B, we would have, so this is for A equations. In the B, we just really have one, so B, the x is nothing, and the y is FG, because I said down was positive, minus f of t equals MBA. And again, positive because down is positive. And we want to solve for the acceleration of the system. So, I think our strategy should be solve for ft. This looks easiest, right? You just add that over. And then plug into that. Okay, so let's do just that. So ft minus fga sine theta, sorry, trying to remember this, MAA, yeah, cool. And then so we're just going to add that guy over. And then we're going to move this, so now we have FGB minus FT equals MBA, okay? So we're going to take this, plug it in there, and solve for A. So all these multi-body problems kind of work similarly. Solve for tension in one, and then you solve, and then you plug in to solve for acceleration in the other. Okay. Add that over. At this point, this becomes, and this becomes, so this is MB times G, this becomes MA times G with the angle, and then we can pull out the A's, so it's MA plus MB times A. And now we just divide this over, so we get our acceleration is MBG plus MAG sine theta over MA plus MB. And we can go ahead and make this a little bit simpler by pulling out the G's. MB plus MA sine theta over their combined mass times G. Oops, this was an A, sorry. Okay, so now does this make sense? If you remember, this was what we got for the Atwood's table, right? Where it was just this system where you have the box connected to another one dangling. And so we get that back if we set theta at 0. So theta equals 0 means we get this back. So we go from, whoops. So I think ours looked like this. And so if we bring that back down, we just get a table again, which is kind of what our solution shows us. Okay, so that's great. It shows that it works because sine of 0 is 0. So good work. Our equation actually works. And of course, the same stuff also typically works where if you make one of the masses ridiculously large, like if we make MB's the dangling mass, right? So if we make mass B super large relative, it would be MB over MB, because MA wouldn't be worth anything, and then it would just be accelerating at G, right? So we can do the same stuff that we could do before to analyze this. And we see that, yeah, it looks like it works. So now let's get a value for it. MB was, I forget, 10 kilograms. So we've got 10 plus MA, which was 5 kilograms. Sine of, I believe we were on 30 degrees. Yeah, 30 degrees. So sine of 30 degrees is just 1/2. That's why I use it all the time. Over 15 kilograms. This is times G. So 5 times 1/2 is 2.5. So that's A equals 12.5 kilograms over 15 kilograms times G. And this is, 9.8. And so if we do the math on this, we get that A equals 8.16 repeating meters per second squared. Great. Okay. So as you can see, really the main thing that changes with these incline problems, we're still doing the free body diagram. Nothing really changes there and won't for any force problem. The only thing that you really have to watch is that you'll get sine with x and cosine with y. Okay. But do check it each time. Do check the geometry of the situation and make sure what you're doing is right. Make sure you're making an angle with the y-axis, not the x-axis. That's another mistake. But other than that, that should be it. So thank you all for watching, and I'll see you in the next one.